From nuclear engineering to space tech, stay tuned for our guest, Dr. Adam Redwine.
I'm Pam Hoffman, Everyday Spacer.
I'm Jeff Miller, CME Computer and IT Solutions.
At Everyday Spacer, we show regular folks how to personally and directly participate in space exploration, science, and astronomy. We're here on Friday nights at 9 p.m. Pacific Time, 12 midnight Eastern Time, and 5 a.m. on Saturday in London. We're broadcasting live from Thousand Oaks, California. Thank you so much for being here. And you want to do this part? One thing quick, Adam, and then we'll have you.
Yeah, so no real cybersecurity news right now, but on the 25th of this month at noon Pacific Time, I'm doing a cybersecurity Zoom with Q&A. So if you want to tune in there and ask any cybersecurity questions, we'll be there for at least half an hour, maybe an hour if people have enough questions.
Make sure and get on the list, Jeff at cmeit.com. I'll figure out for this.
So our guest is Dr. Adam Redwine. We'll be back in 8.3 seconds. There's a link to that book in the description. If you want a signed copy of the book, write Pam at everydayspacer.com for details. From nuclear-powered rovers and reactors in space to future lunar power plants and nuclear propulsion concepts, Dr. Adam Redwine is a physicist and a nuclear engineer whose career spans nuclear fuel processing, naval reactor analysis, high-energy physics, and radiation detection R&D. He has several science degrees. Adam brings deep insight into nuclear technology and its space applications.
Beyond the lab, Adam is a private pilot, world traveler, motorcycle rider, gardener, and former astronaut applicant. We better hear from that. So welcome, Adam, or should I say Dr. Redwine? That's a freshly minted PhD, I understand. Where would you like to start with all of this?
Oh, where would I start? Well, thank you for having me. I appreciate it. We can start, I suppose, with the end, with the recent PhD. So let's talk about that that academic area. So I don't know if you want me to just jump into it, but I'm happy to give a brief overview and then let you ask questions, maybe.
Sure.
Let's hear from. We got a couple comments going. Let's go there first.
Oh, sure.
We like to say hi.
Hi, Jamie.
Sure,
Hey, Jamie.
Hi, Don.
Hi, Don. Welcome. There you go.
Okay.
Our audience is so nice. Now, go ahead.
Sure. So the work that I did was for a collaboration called the NEXT project. This is looking for a particular type of radioactive decay. And the reason why this decay is very interesting to us is because it can only happen if the neutrino has a very specific property. So the world is made up of all sorts of particles, and some of them are particles that you may be familiar with, like protons and neutrons, but those are not actually base particles. They're not fundamental. They're composed of things that we call quarks. But around the protons and neutrons, you have electrons. Those are fundamental particles. And then we also have fundamental particles that you might not think about, like photons, and others that you just probably don't hear much about, like neutrinos. And neutrinos have some very interesting space applications. If you are unfamiliar with the neutrino telescopes, like the one in Antarctica, you should definitely look into that, called IceCube.
There's some science projects around those. I think we've talked about a couple.
Yeah, they're cool. I know a little bit about how that kind of stuff works also, so we can certainly talk about it.
Nice.
The neutrino is a very interesting particle. It was kind of the last one to be discovered, and we really don't know very much about it because it basically only interacts in one of the very rare ways. So we say there are four fundamental forces of the universe: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. And most of what we observe in our daily lives are due either to gravity, where you drop things, which is apparent because it's only acts in one direction. There's no anti-gravity, however much you might want to want to have it. It only goes one way, so it all adds up. And then the other one that we really interact with almost exclusively is electromagnetism, which is what drives all our chemistry and electricity and all this kind of stuff. But as far as the actual like binding of these quarks into neutrons and protons and everything, this is mediated by the strong nuclear force, which is kind of what holds things together. And then for radiation purposes, for the kind of stuff I do, there's a fourth and very important force called the weak force, which instead of holding things together, breaks them apart. And neutrinos basically only interact with this weak sector, we call it. And so because they don't interact with electromagnetism, they're electrically neutral. Because gravity is so weak, and because the weak force is appropriately named is weak, they're very hard to detect. So we don't know very much about them. We know that they have a little bit of mass. We don't know what the mass is. Yeah, my dog is playing in the background. But
somebody's a cute dog. Hi,
yeah,
Jessica. Welcome.
he is. So matter has a natural counterpart called antimatter. And for most particles, the antimatter version is the exact same thing, except with all of the signs reversed.
Right.
So an antimatter electron, it's called a positron. It's exactly like an electron, except it's electrically positive and has some other things that are reversed too, but we don't have to get into the details. Neutrinos are really important because of their properties, they actually don't have signs because they're neutral. They don't interact with these forces, and because they don't interact with the forces, they don't have signs. And so it could be the case that these particles are their own antiparticle.
Oh.
So that a neutrino and an antineutrino are actually the same thing.
Wow.
And if that's the case, then we should see this particular type of reaction that we're looking for. And so that's what the search that I did my PhD work on was for.
Oh, so are you looking for a neutrino?
So yeah, so the thing is, neutrinos are, like I said, they're almost impossible to detect. And so if you have something that's very, very hard to detect, then how are you going to show that you have not had one? The thing we're looking for is something that does not emit neutrinos. We're looking for a specific reaction that emits 2 electrons, but 0 neutrinos. And so, you know, you could imagine, well, you could say we set up some situation where we expect a certain number of neutrinos, and if there's some missing, then we'll see fewer then. So that would be one way to do an experiment where you find something where you have no neutrinos. But neutrinos are almost impossible to detect. So you could never reliably say, well, we see fewer neutrinos than we should because some are missing. Like it's just statistically impossible.
Right.
And so what you have to do is find an interaction where there are no neutrinos, but where you can detect something that's physically meaningful and related to the absence of neutrinos. So the way that we do that is so there's a type of radiation called beta decay. So a beta decay is when a particle emits either an electron or a positron. And in some cases, the mass difference between the parent and daughter won't allow single beta decay, but you can have 2 beta decays and take it from the parent to a granddaughter product. So you can emit 2 electrons at the same time. Now, if you do that in the traditional theory, in the standard model that we use, that also requires emitting antineutrinos, because this is it's how you balance interactions. It's sort of just a fundamental part of how the standard model works. But if neutrinos are their own antiparticle, and you have 2 times this decay, so you're emitting 2 electrons and 2 antineutrinos, but these antineutrinos are themselves neutrino-antineutrino matter-antimatter pairs,
Right.
then what could happen is you could have two electrons emitted and the neutrino cancels, so that the two neutrinos cancel each other out. And
So it
if that,
disappears, or
well, yeah, I mean, yes. When you get into quantum mechanics, it's very complicated. So I will accept that's a reasonable interpretation. Yes.
we love all that stuff. So just
Yeah,
so you know.
yeah. What it means is that all of the energy. So there's a specific energy. The difference in mass between the parent isotope and the daughter, or the granddaughter in this case, the difference in mass sets the amount of energy that you have. Like that, it's just this conservation of energy.
Yeah.
And in this particular version, where there are no neutrinos, all of that energy has to go into the electrons. And so you have two electrons with a very, very specific energy, because it has to, like, these are the only things that are carrying away energy. And you can detect electrons because, electrons interact with electromagnetism. And what's more, you can detect how much energy an electron has by a variety of different ways. So if you're looking at these kinds of decays, and you find that there are more than you would otherwise expect with this very specific energy signature, then you can say we have shown that there must be these extra events occurring because there are no neutrinos. So that's the approach.
Okay,
Yeah.
so just conservation of energy, they aren't colliding and producing something else. They're canceling each other out, and the energy has to go somewhere, which is the electrons.
So
Yes, that's a perfectly fair description. Yeah.
This is the non-degreed explanation.
Correct.
So it's sort of like
yeah.
electron plus.
Yeah, I mean the thing is, like in quantum mechanics, like in modern, it's weird even now, because like now we talk about classical quantum, classical quantum, which is like strange because quantum is like the new thing, but the modern approach to particle physics is actually quantum field theory. Particles are a thing, like, so it's hard to say like, the particle exists and then doesn't exist, or they collide, because like, well, yeah, but I mean there aren't really particles. Like particles don't exist. It's just fields. So like, that's close enough. Like this is, but honestly, I mean, even we talk about it that way. We do say, it's this particle or that particle. So yeah, you don't have to get too pedantic. But
we have a bunch of comments. Can you
please
pause a second for me? Okay, good.
So
Thank you.
Start with Janie. Dogs are like toddlers. They want your attention when you're on the phone or on Zoom with others.
Yeah.
Yep.
He doesn't like that I'm talking to other people.
Right.
Yeah. Okay, and Cliff says, "Hi guys, sorry I'm late."
Hey Cliff, welcome.
Yeah. And Dan shows.
Oh, good.
Says,
hey Dan.
The case of the missing neutrinos. Hello, Dr. Redwine and all. Also, he says, could some missing particles have gone time reversed?
I'm happy to address that actually. Yeah. So in the case of neutrinos, no. But it actually raises an interesting point, because, so again, to sort of get into the way that modern quantum field theory works, is that the difference between antimatter is this switching of the signs. And if you know sort of the approach of relativity to space-time, is that space and time are basically the same thing. There's just one key difference, and that is the sign. And so in typical particle physicists work in what's called a mostly minus system, where they represent space dimensions with a negative sign and time with a positive sign. And all the equations that we use apply to all four of those dimensions at the same time. So when you write an equation that sort of accounts for this space-time effects of relativity, you write them in a matrix form where you have actually it's a set of four equations together. So this is how mechanically we do modern quantum field theory. Well, but again, I said the difference between matter and antimatter is flipping the signs. And so time is just one of those signs in the equation. So in principle, why can't you just flip the sign of the time signature? And in fact, that actually works perfectly well mathematically. And so there are people who would argue that a positron, so like an anti-electron, is actually just an electron, but moving backwards in time. And other antimatter particles for the same. And in fact, it actually raises a very interesting cosmological hypothesis that I heard about not long ago, where because of this particular feature where antimatter travels backwards in time and matter travels forwards in time, a physicist has recently proposed that it could be that at the Big Bang, you actually had a separation of matter and antimatter, not because of annihilation or something like this, but because the matter went forward in time and the antimatter went backward in time. That there's actually a parallel universe that also originated at the Big Bang, but is just traveling the opposite direction in time, but is otherwise identical to ours. And for them, our particles are their antimatter.
That's why we don't have very much antimatter here.
Correct. Yeah. So it kind of neatly explains.
Good explanation for it. Yeah.
It is. Yeah. It's very interesting hypothesis. It's relatively recent. I'm not. Like any hypothesis, you're going to have to develop predictions and take measurements and all that fun stuff. But
yes,
the theory is cool.
We got some more comments. Hang on.
Yeah.
Sure.
Hey, Naomi, welcome.
Yeah.
All right. Yeah, very interesting. And Donald's here. What kind of detectors are you using now? Version 3 flavors. Wait, 3 flavors have been found.
Yeah. I think the V there was a sort of a new. So we represent a neutrino with a new Greek letter new.
Oh, I see.
Like a V.
Yep, got it.
I suspect that's what he was going for.
Probably.
So we are not we're not looking for different flavors. Our particular interaction just addresses electron neutrinos, but it doesn't actually matter that much because the flavors are really just different mass eigenstates. So the actual flavor is not particularly relevant. Sort of. It's relevant to our likelihood of success, but is not necessarily relevant to the experiment per se.
Interesting.
And then, sorry, what was that? What kind of detector are you using? So, good question. We are using what's called a time projection chamber. This is a technology that was developed by a professor named Dave Nygren, who was actually one of the co-founders of the project that I work for. He developed this in the 1970s. It's now a very commonly used detector system in particle physics. And I can give you the basic overview. And let's see, I might even have good slides for this. Yeah.
Do you know the song about? Do you know the song by Hawkwind about all this stuff? It's pretty funny.
Think so. Let me share screen. Okay.
Can you get it?
Screen. I'm getting it right now. So let me know if you can see. Can you see slides?
Got to add it. There it is.
Okay. You can see a slide that's up here with a picture on the right?
Yep. Next time projection chambers.
Yeah, so this is a time projection chamber. This is based on the detector that we used for what most of my dissertation work was on. This is now our old detector. We have a new one that's currently operating.
Okay.
This is called the Next White detector. Now you have a stainless steel container. That's the outside container. And then you have an anode and a cathode on either end of this interior volume. So anode and cathode just means they're electrically charged. So these are like grids. You think of it like a chain link fence. It's very small. These are tiny grids. And they have, you can see voltages here. So a difference of several thousands of volts across them, which establishes an electric field inside the volume. Now you even that field out by using what's called a field cage. This is the sort of dots on the edges. These are copper rings that sort of slowly adjust the voltage from one to the other. It gives you a nice even electric field. And then when you have an event that happens inside of this volume, the electrons, which again are the things that we can detect, the electrons excite and ionize gas that's inside the chamber. So they will rip other electrons off of the gas, or they will interact with it in a way that brings its energy level up, and then the energy level will fall back down. And when the energy level falls back down, it emits photons. It emits them in the very near ultraviolet. So we actually downshift those to sort of visible wavelength. So you get a little teeny flash when your event first happens. And we detect those with photomultiplier tubes. This is the side on the left. And those give us timing information. And then because you have this electric field and you have all these free electrons and now ions, they want to move along the electric field. So the electrons want to go towards the anode, and the ions go towards the cathode. And so as these electrons drift through, they eventually get to this other end where we have this gate and a small gap where we have a very high electric field. And this high electric field is enough to produce more excitations. And so you're getting these free electrons are colliding with the gas in this little gap, and they excite them, and then again they de-excite, and they produce a little flash of light. And you can pick up this light with a silicone photomultiplier. This is the right side panel. And because it's a three-dimensional shape, so this cloud of electrons, it passes over time. Like it takes some amount of time for it to pass through this gate system. And if you cycle your SIPM, so you're taking pictures very, very rapidly, you can take one picture as the front of the event comes through, and then another picture as the middle of the event comes through, and then another picture as the a tail of the event comes through, and then you can reconstruct in 3 dimensions what this cloud of electrons looked like, and so you get a 3-dimensional particle decay. It's very cool, and I can show you exactly what it looks like. So this is sort of low resolution stuff. This is simulation. To give you an idea, this is data. So actually, this is these are Compton scatter events, but this is 3 different axes that you're looking at this data from, and these are actual particle interactions, and these are particle antiparticle decays. So this particular set of events, these are 2 different events looked at each from 3 different dimensions. So one of these particles in each of these events is an anti-electron, a positron. So yes, that's what our data looks like.
Wow, that's amazing.
Really?
Oops.
So, whoops. Oh, we lost Adam. He'll come back.
Yeah, because we have more questions for him.
We sure do. And I know sometimes when people remove their, when they stop sharing.
Yeah, he didn't stop sharing. He basically.
Yeah, he left. Add to stage. Hello, welcome back.
Thank you. Click the wrong one.
Yeah,
that's okay.
Okay.
This is a good break because
we got questions for you.
Excellent.
But, yeah, NAMI has 2 panels. Here's the first one. Sorry if this was already mentioned. I was a bit late, but wasn't there an experiment error a few years ago? Go ahead with it. I think it was called the Opera.
Sure. Yeah. So they looked all through their experiment to try to figure out what was wrong and couldn't. And so they published on it, basically saying, like, our data says they go faster than light. We don't believe our own data, but we can't find the problem. Please help. And so then you had this whole flurry of papers of people trying to figure out what went wrong. Ultimately, it turns out that there was a wiring issue. Like one of the connectors was not quite wired correctly or something. And because of that, the timing information was wrong.
So it's kind of noise
the clock,
in there, basically?
Yeah, so the clock was off because something just wasn't quite plugged in correctly.
Okay. Yeah. You up for another? Donald's got a.
Yeah.
There you go. How are downshifting from UV to visible light? Sorry.
Yeah. Triphenylbutadiene is how we're doing it. So there's a variety of.
Is that a chemical?
Yeah. So there's a variety of chemicals that will do this. And the very near ultraviolet photons interact with this chemical and they excite it, and then some of that energy is dissipated by other mechanisms within the chemical, and then so the de-excitation has a little bit less energy. which shifts to the wavelength. So the light that it emits, and so it's like when you have those stickers like they charge up in the sun and then at night they glow green or whatever. It's a similar sort of process. And so so it's this kind of it's called a wavelength shifter.
Yeah, it's like a coating on a fluorescent tube.
Oh.
Yeah.
Taking the UV down to other frequencies.
Yeah.
But does that add a delay? Well, I suppose you know what the delay would be in that.
So there's complications with all of this, both delay and also potential loss of light. So because when I say that we can measure the energy of the photons, the way that we are doing that, like the actual data that gives us how much energy the photons had, is the amount of light that we collect. So more energetic will produce more light because they are making these excitations along their path of travel. And so, if you have more energy, your path is going to be longer and you're going to excite more. And so we look at the quantity of light is our measure of energy. And because energy is fundamentally our signature, we're looking for an excess of events that have this very specific energy. It really matters a lot, like exactly how much energy you have. And so if this chemical is reducing the amount of air or altering it in some way, like you really need to know these things very quick. So these are the kinds of things that we have chemical engineers who work with us, and they get their PhDs in chemical engineering and they do these studies and publish on that kind of stuff. I'm not on that end of things, but yeah, we absolutely have people in the collaboration who do that sort of analysis.
Naomi says, thank you, Adam. That's good to know. So they definitely don't travel faster than light.
Correct.
Right?
They don't travel faster, but so we should take a moment, especially on this for you guys. So I talked about neutrino telescopes, and they can be really, really important as signatures in astronomy, because I said neutrinos basically don't interact like almost at all. In fact, I'm going to get this. I'm going to get the number slightly wrong, I expect, but I think the average neutrino flux at Earth is something like 10 to the 24 per square centimeter. So your thumbnail is about a square centimeter. So at any given, there are trillions of neutrinos passing through your thumbnail, and that's just true everywhere. They're all over the place.
Right.
So
which is amazing that so few interact because there's so many.
Yeah, they're trillions and trillions and trillions of them, and they basically just don't interact at all.
Yeah.
But this is really cool because if you have something like a supernova, one of the early processes in a supernova is some of these nuclear reactions where you're emitting neutrinos for exactly the same sort of reason I talked about earlier, where you have to balance. So there's conservation of quantum number kind of stuff, where you're emitting neutrinos in order to keep a balance of the right numbers of particles. And so you have a supernova, a star collapses and emits a ton of neutrinos from its inner core. And those neutrinos basically just fly out because they go straight through the whole star because they don't interact with anything. And so you get this giant burst of neutrinos that comes out immediately. And even though they don't travel faster than the speed of light, they actually still arrive before the light from the supernova, because the light is also emitted by these same processes, but the light can't just escape. The light interacts with the particles that are next to it and then heats those up, and then those interact, and the light bounces all around, and it takes a while to get out of the star.
That's normally right, that happens normally with the star anyway. Like our star.
But if it's an ongoing process, you can't distinguish between the two, right? But if you have this sudden collapse where you get a burst of them, then neutrino telescopes. So if you have just one, all you can say is, "Hey, something happened." Yeah. But if you have several of them, and you can say, this neutrino telescope in Antarctica saw this, and this one in the Mediterranean saw that, and this one in wherever saw this other thing, then you can triangulate, and you can say a supernova happened right there. Turn your telescopes, and all the telescopes turn and look, and they can watch it happen. So it's very cool.
Wow, that's fascinating.
Yeah, so
Right on.
so it doesn't matter how far away it is because the gap isn't in the speed of the particles. It's just when they were emitted from the star itself.
Right, Naomi?
Yeah.
That's really cool. Oh, I'm so glad we had you, and I'm thinking we're going to have you back again because, I mean, all these different degrees you have, and do you have any aspirations for future degrees, or have you hit your
No,
limit?
I think PhD is enough for me. Honestly, I wasn't even real keen on getting the PhD, but yeah, I mean, I guess in theory I could go get a business degree or something, but I don't care. Like the R&D work is fine.
You can
Yeah.
get another PhD in something else. I know people
Yeah,
that
no
do
thanks.
that.
No thanks. Yeah, I know people who have. A good friend of mine here, she had a PhD, and then she was living in Norway, and she wanted to stay, but didn't have a job. But if you were a student, you could live there with a student visa, and so
I
she
see.
started a second PhD, and she did that for like 3 years or something, and then I forget exactly what it was. Like she ended up getting her citizenship in Norway. She's like, well, I don't need a second degree, so she never finished the second one.
Oh,
Yeah.
crazy. Interesting.
Yeah, that's
So
tough.
you've had so many adventures. I mean, just looking over all the different things you put in your bio is like, oh my God. And like all over the world, it's very,
Well,
Yeah,
very
yeah. I've
well-rounded
lived
scientist.
in 5 different countries,
Yeah, okay,
in 8
got it.
states. So I get around.
Yep. I definitely like to live
Well,
in other places too.
6 if you include Texas.
Yeah, quite exactly.
So let's see. Donald says, how have all the
Neutrino flavors.
been accounted for by the standard model?
So yes and no. It depends a little bit on who you ask. So there was actually a Nobel Prize given, I think, early 2010s or something, basically showing that there are no more than 3 generations. So, which actually I should probably get into a little bit for those who don't kind of know where this is coming from. So, okay, so I said we had fundamental particles like quarks and electrons, and then we have others like photons, which are bosons, and neutrinos, and this kind of stuff. So apart from the bosons are what we call mediators. So the electromagnetic force is mediated by photons. So if you have 2 magnets and you can feel them pushing against each other or holding each other or whatever, the force of that, what's actually making that happen is photons. So photons are the things that are making this interaction happen.
Wait,
In
photons?
the case of gravity, yeah. In the case of
Okay.
gravity, presumably you have gravitons, which we have not detected and probably never will, for a different reason. But yeah, so presumably you have gravitons. And then you have the strong nuclear force, which is mediated by what we call gluons, and the weak nuclear force, which has a few different mediating bosons. Okay, so these are the bosons. They mediate the forces. The forces are sort of between, well, they interact in complicated ways. But we have these particles like the quarks and the electrons and the neutrinos. These are fermions, and you have the first, what's called the first generation. This is the up and down quark, the electron, and the electron neutrino. So these are 4 particles, and they each have their own particular mass. They have different charges. Electron has 1 electron charge, obviously. An up quark has positive 2/3, and a down quark has negative 1/3 electric charge or something. I'm pretty sure that's right. Neutrino has no electric charge. And then you have, oddly, perhaps, another set of 4 particles that look just like this first set. So these are the strange and charm quarks, which sort of are similar to the up and down. You have the tau, I think that's right. I always mix up which generation's which for the electron, which is kind of like the electron. and then you have the tau neutrino, which is like the electron neutrino, and then you have one more generation, which is the top and bottom quark, and the mu and the mu neutrino. Again, grain of salt on that. You can look up the standard model particles.
Right.
The difference, so the charges are the same among these three generations. What's different is the masses, and so the first generation is the lightest for each of these. The next generation is heavier, and then the third generation is heavier still. And because some mass is, there's a mass energy equivalent, so this is equals mc squared. This is Einstein. A more massive particle can, with conservation of energy, can decay to a lower mass particle by emitting something else. And so when we look around in nature, almost everything is this first generation, these low mass. This is the up-down electron and electron neutrino. Like almost everything in the universe is this particular slice of the particle world. But we can, in particle accelerators or whatever, we can pump a bunch of energy into these particles and smash them into each other, and then we get all these little exotic coming out of them. And so we can create these other generations of particles. And it's this difference is what he's referring to when he says flavors. So I'm calling them generations. The generation refers to the whole sort of set of particles. Neutrinos, again, are kind of the odd one out. So they don't get their own name. They're just named after the electron equivalent for that thing. Neutrinos are a little bit strange also because it's kind of a naming convention thing, actually. Neutrinos, again, particles don't exist, despite all of this description of particles. In between interactions, particles exist as a quantum superposition of different, what we call them eigenstates. And so the neutrinos exist as a quantum superposition, and the probability of detecting them in any particular state is a function of the amount of time or distance between the 2 points of interaction, where they were generated and where they're created. This is actually how we detected, or this is a important part of how we detected that there were different types of neutrinos in the first place, because when we were looking at neutrinos coming from the sun, we expected a certain amount of them. My dog. We expected a certain amount of them, and we didn't see them. We were missing neutrinos. So this became called the Solar Neutrino Problem. So I've got. Could you put the question up again? So this is the background of like what he's talking about when he says flavor states. Okay, so how are they accounted for? So the standard model, traditionally, at least, it treated neutrinos as though they were massless, not because it was required, but mostly just because we didn't know any better. And so we needed a mass for the neutrino, so we just put in 0 because it makes things easier. So we didn't know. And if it had a really high mass, we would know, but we didn't. So we just used 0. And then because of this difference in our detected neutrinos and the expected neutrinos, it tells us that there are these different mass eigenstates, which means that it has to have non-zero mass. If there's different mass eigenstates, then the mass can't be 0.
So not virtual mass.
Different from 0. Yeah, so we know that neutrinos have a mass, but we don't know what it is. We just know it's not 0.
And it's probably pretty darn small.
Yeah.
It's a very small, yeah. It's a tiny fraction of the electron mass, which itself is very small. Yeah, so we also, so there was a particular ordering. So I said previously you have this first generation is the lightest, and the second one is heavier, and the third one is the heaviest still.
Right.
That is the case just by convention. I mean, it's just how we name them, is the heavier one gets the higher name. But the gap between them also could be different. So normally speaking, the first generation and the second generation have relatively similar mass, and then the third generation has quite a lot higher mass. And this is called the normal hierarchy. But because we don't know what the neutrino masses are, it could be the case that you have one very light neutrino and then two or two that are heavier but are closer together. And this is called the inverted hierarchy. And it's actually very relevant for the experiment that I worked on because it has a big impact on our probability of discovery. So we would prefer the inverted hierarchy because it increases our probability of finding it. But, you know, it's called the normal hierarchy for a reason. If neutrinos are like the other particles in this particular regard, then it's going to make it a lot harder to detect. So this is how the standard model accounts for them. Treats it as zero mass. In practice, it's not actually zero mass.
Got it. Your dog is being so good.
He's not.
A little bit of whining, but otherwise, fantastic. He's not up on the keyboard and jumping around and barking.
He's staring daggers.
He's a good boy.
But what, you know, to ground this a little bit, what would all of this actually be useful for? What could we do or learn about the universe by knowing this?
I love that question. I love it a lot.
Well, it's useful to know things. From an engineering standpoint, probably not a lot, because because again, neutrinos, they're like almost impossible to detect. But again, you know, understanding how neutrinos behave allows us to do things like develop these neutrino telescopes, like the ones that will allow us to point telescopes towards supernovas faster and stuff. So like the only reason that you can build a telescope like IceCube in Antarctica and understand what the data that you're looking at tells you is because we understand what we do. So that's, you know, it's kind of a roundabout way to think about it, but I think that that's actually the right answer.
That's very practical. I mean, it's really
it's not like we can take neutrinos and like build a building out of them. You know, it just doesn't work that way. But our knowledge allows us to build the next generation of equipment and detectors and accelerators and telescopes and all that kind of stuff. Yeah, exactly.
Would better understanding allow you to go over, like for future understanding of neutrinos, allow you to go over the data that's already been collected and get more out of it? Or would the current data probably be too clunky for that?
It's a good question. I suspect the answer is probably not very much. In astronomy, you do get that kind of thing a lot, where you can still look at old pictures, old astronomical plates, and like learn new things, or you can say, oh, this based on the orbit, we should have seen it. And with neutrinos, because the interactions are so rare, and because you really have to know what you're looking at, like it would be very unusual, I think, that you could get, there may be an odd case here or there where maybe something happened so for example, you get these weird, detection events like the oh my god particle and stuff, and like maybe somebody looks at it with fresh eyes and realizes like, oh, well, maybe this could be explained by a neutrino interaction or something like that. I expect there's not a whole lot of cases where that's going to be the case. Again, just mostly because detecting neutrinos is such a challenge, and because it's so difficult. I mean, we really have to go out of our way to have any hope of detecting any of these at all. It kind of means that something that wasn't built to do it specifically basically has zero chance of being affected
better
by
detectors. Them. Better detectors is what you get out of it.
Okay. All right. We've been at this almost an hour. I would absolutely love for you to come back and talk about more stuff if you are at all willing. I think
sure, anytime.
There's a big list. We're never going to get through it all tonight.
Yeah, you've done so much stuff, and you've worked on so many different things that I mean, just the motorcycle flying, and I'm assuming you drive cars, so you've done two, 3, and 4 wheels.
Absolutely. Yeah, for sure. Yeah, I
You need
haven't flown in a lot of years, but I like it. It's very expensive. So I currently live in Israel, and I looked into transferring my pilot's license here. To my understanding, the licensure requires that you take a test that's all in Hebrew. And while my Hebrew
Okay.
is getting better, it's not quite that level yet.
Mhm.
Interesting.
Well,
All right.
Yeah.
yeah. You should learn how to ride a unicycle. Then you can go 1, 2, 3,
Oh
and
boy.
4 wheels.
So my oldest brother, there is a unicycle convention, annual unicycle convention not far from me that I've been to several times. I have ridden around there. Um, my oldest brother was actually a big fan. He had a couple unicycles actually. He lived in Lebanon for years, and
Mm,
he would ride his unicycle to university in Lebanon, like just on the sidewalk. So, and he would get a lot of
nice.
stares. Yeah.
Okay, Donald has come up with another question, or well, a comment. I've been following the work
Yeah.
of Dr. Smith at
Yep.
ERAUPR. Is that, I don't know,
Yeah.
is that
MiniBooNE.
Every riddle? I think it's ever. I.e. MiniBooNE experiment at the Fermilab search for massive neutrinos.
Yeah. Yeah. So I think MiniBooNE is decommissioned, and
Oh,
they're moving to the next set of this same experiment. So
hmm.
yeah, actually, just yesterday I was at a mini workshop, and they were talking about MiniBooNE. So they use TPC technology, time projection chamber technology, in their detectors. Their TPCs are like the size of shipping containers. So they have these
Wow.
giant grids on them. So it's really cool because they're looking at these very big events. Again, the events we're looking for are very small, and they're span like a centimeter. It's a couple of electrons through high density, high pressure xenon, so they don't travel very far. But when you're looking for neutrino interactions, they are very high energy, and when they do interact, they cover a very large area, and so you need really really big detectors, like huge. And so because you need such gigantic detectors, you have to use material that you can afford, because even countries like the US, like, you're not going to spend trillions of dollars on your detector, so you need to have something that's affordable. And
Mm,
so you have, like, IceCube that I mentioned a couple times.
yep.
They use the Antarctic ice shelf as the detector material, so it's
Yeah.
free because it's there, the ice shelf, and then you drop detectors down in, you drill cores and drop down. MiniBooNE and MicroBooNE, and it's a whole family of detectors.
Oh,
Uh, they use I think it's argon. Yeah, I want to say it's argon. I think they use liquid argon, which is not prohibitively expensive. It's not free, but it's a sufficiently affordable with enough millions of dollars.
got it.
Uh,
Not trillions either.
yeah. Millions is pretty affordable at this for this kind of high energy physics experiments. Millions is quite affordable. Um, yeah, so the experiment is at Fermilab. They have an accelerator, and they are producing a neutrino beam, basically. So they're accelerating particles and slamming them into a concrete block, and they're aiming down, more or less, or angled down, and the neutrino beam passes through detect a series of detectors. This is the MiniBooNE, the container size things I talked about, and they can look for interactions and then tell properties of the particles based on this. But because of the angle and direction, that beam goes straight to South Dakota, where you have a
Oh,
very big mine. It was a giant gold mine called the Homestake Mine. It was actually the largest, the most productive gold mine, I think, in the world. Something like 10% of all of the world's gold came out of this one mine.
wow.
And the mine has been shut down, doesn't produce gold anymore. But they had this giant cavity in a mountain, and they turned it into a physics experiment
I
lab.
love it.
So it's called SURF, which I forget what the acronym stands for. It's just outside of, where is it? It's in western South Dakota. I don't remember the city at the moment,
You
but
said surf or jerf?
SURF, SURF,
Surf.
SURF.
Okay. Okay.
Yeah. Let's see, SURF lab.
Sometimes the audience finds that for us too.
Sanford Underground is lead, South Dakota. Anyway, so
how does this work in a gold mine? I know, like a salt mine, it can fill with water, and they put the detectors all over the place.
Yeah. I mean, it's the people go down into the mine and say it's like just a laboratory that's under there. So the detector's not filling the mine per se.
Okay.
Which they kind of did with Kamiokanda in Japan, which also can do these kind of experiments. No, so the neutrino beam goes through this laboratory in South Dakota, and then they can put similar detectors there. And so you can have detectors that are looking at the exact same beam, so the near detector, and then far away, the far detector. And as I said before, in between interactions, they exist in this superposition of eigenstates, and the properties are a function of the interaction of the distance between the two interaction points. And so if you can statistically look and see, like, okay, the close by interactions have this set of properties and the far away ones have this slightly different set of properties, you can leverage the statistics to make statements about what the properties are at a fundamental level.
Neat.
So yeah, it is a very cool experiment.
Yeah.
Also, Boone is my middle name, so my colleagues all say I should have worked on that one.
Yeah. And just out of curiosity, and I don't know if you would know the answer to this, but you said that, ice is cheap, argon is not quite as cheap, but I'm assuming is a better medium. If you had unlimited budget, is there a medium that you would use for this?
Wow.
It's a great question. I don't know. I'm sure there's something that is more favorable than argon. Yeah, but argon is reasonably good. I mean, it's been used for a long time. It is
as a noble gas. You don't have to worry about it.
So exactly. So it is pretty good. Like I said, the experiment that we uses xenon, which is very favorable.
That's really also a noble gas, right? Xenon is a noble?
Yes, and it is extraordinarily expensive, like just mind-bogglingly expensive. And we are using, in our current experiment, we are using 60 kilograms of it. I want to say that. Is that right? Yeah. And
can you keep it contained, though? Can it stay there and it persists?
Yeah, I mean, so xenon is relatively high up in the periodic table, so it's relatively large in the atomic scale. And because it's large, it doesn't like pass through things. So, for example, hydrogen is notoriously difficult to contain.
Oh yeah.
Because it's just it's a proton electron, and it can just kind of weasel its way through things. So hydrogen is actually relatively difficult, but like xenon's not. It's not particularly hard. You have to be really careful with it, mostly because it's just so awful expensive. You don't want to lose anything. And for our experiment, we're using enriched xenon. So it's xenon that's been processed through centrifuges, like they use for enriching uranium and all this kind of stuff. So it's extraordinarily expensive.
Wow.
Yeah, we want to move up. Eventually we want to move up to the ton scale if we can. So we'd like to get a full ton of xenon, a metric ton.
Wow.
Which is
on the order the scale, won't it? The scale of what you did try.
Absolutely, yeah. So it's on the order of hundreds of millions of dollars for that much xenon. So. All right, so I said we're looking for this particular interaction, right? We're looking for this neutrinoless double beta decay, and it's an ultra rare decay. Like in theory, we think it may be able to happen. We hope it does, because that's what we're looking for. If it does happen, we know for a fact already we've excluded some region of the sort of the parameter space. We know for a fact that the half-life of this decay is greater than 10 to the, I think I want to say 26 years or something like this. And to put that in perspective, the universe is much less than that. So if you had if you had one of these atoms and you watched it for the entire age of the universe, and you did that for every year that the universe has been in existence, you would have less than 50% chance of seeing it decay.
Mhm.
So, yeah, so it's very, very rare. So the only hope that you have of ever seeing something that's this rare is to not have one atom, but to have trillions of them. And so you get a ton, as much xenon as you can pack into a system, and you just put trillions and trillions of xenon atoms together, hoping that a couple of them decay. And we are expecting something on the order of 3 to 5 decays per year with our 100 kilograms or whatever. So
you're going to detect that too, I take it, right?
Yeah.
Yeah.
Maybe?
So I mean, yeah. So like if you have this much material and you only have 2 or 3 decays over the course of a year, you need to be really sure that you don't miss them. So you have to be really good about taking your data consistently and looking through it all. And it's a huge amount of data and all this. So you can do other things with the data, right? So like that's ultimately our goal, is to find this one particular decay. But we've got all sorts of data. We can tell you about other kinds of decays. So we can publish about, the actual neutrino full double beta decay and all this kind of stuff. Yeah. So in theory, if you had unlimited budget, maybe you'd like to use something like xenon or something like this.
Is it just the fact that it's non-reactive that's the real benefit?
No, you need to have like the scintillation properties and stuff. So the way that you're detecting it is a neutrino interaction is an interaction in the weak sector. So it's complicated. I mean, it's quantum field theory stuff. So you can calculate the probability of interaction based on the internal atomic structure. So one particular proton is 2 ups and a down quark, and one neutron's 2 downs and an up, or whatever. And then you have an atomic nucleus that has collections of these. But from a quantum scale, the entire nucleus is one system. It's just a little more complicated than that, because the quarks are bound very tightly, hence the strong force. Is what it's doing, is binding these together. But like you can't treat it as separate stuff. It's all one system. And so if you want to do the calculation of the probability of interacting in the weak sector for a neutrino, these are very, very complicated calculations. And pardon me, but like it's the kind of thing that people will do numeric simulations for, and people will run supercomputers to try to analyze. And you get different publications that will have slightly different values, and then the ones that we think are most reliable will gather together, and there's publications about atomic probabilities and stuff. So those of us who are in the field know which references to go to, and then they'll say, okay, here's the properties for this particular atomic system, and we are drawing from these particular research papers and all this kind of stuff. But like, when you get to that level, it's beyond the sort of just reading the textbook and saying like, oh, this is the right answer. Like we don't know what the right answer is. That's why we're doing the physics. Like we don't actually know what the probability of interacting is. We can calculate, we think, sort of, and we can estimate given some assumptions, and we can run numerical simulations. But maybe you don't like those assumptions. Maybe they're not right. You don't know. So we kind of have a range, hence the uncertainty bars.
Well, you get enough assumptions, and then you can go into economics.
Yeah, exactly. Yeah.
Here's one more. How do you filter out the noise? That is a very good question.
It is a good question. It's what I spent the last 7 years doing, and I'll send you my dissertation so you can read it.
Yep.
Yeah, it's not easy. So in our case, we have these 3-dimensional shapes, these clouds, and actually I can, let's see what to do. Yeah, let me do this again, and I will try not to jump out of the presentation this time. I apologize.
Well, if you want, let us know and we can take it off the screen.
Thank you. Yeah, here. Okay. Good.
Oh, hold
You
on,
see
I
my
gotta
slides
add it
again? All right.
Yeah,
I
hold on.
apologize.
Here it comes. There you go.
Yeah. So this is actually like exactly what I did with my dissertation. Good. You can see. Okay. Yeah. Here, actually, I give you some pictures of the detector. So this is the silicon photomultipliers. Here's the field cage. This is my colleague Gonzalo. Very cool guy. This photomultiplier tubes on the bottom right here. This is actually in Spain, under the mountain. So our detector is under the Pyrenees.
So this is what you did for school, not for your job, right?
Yeah. This is my PhD work. Yeah.
Okay. Yeah.
So it's right on the border with France. Very pretty area. Highly recommend. I love the Pyrenees. This is the Basque country. So we're deep under a mountain there. This is energy resolution. Okay, so in our case, what we're looking for is these events where you have two electrons. When an energetic particle an ionizing particle in particular. So I said these electrons interact by exciting and ionizing the surrounding gas. When they do that, they give up energy because, again, it's conservation of energy, right? So they're contributing some of their energy to the gas that they're in, and thereby they're losing some energy. As they lose energy, there's a couple different effects that happen. One is that a lower energy particle has a higher probability of a higher angle of reflection, basically. So the angle that they bounce off of is bigger. Which means that the track that they span is tighter. And then also at the very end, you have this particular phenomenon called a Bragg peak, where the amount of energy that's deposited per distance traveled increases very high right at the end. So it's like if you're driving and coming up to a stoplight and you put your foot on the brake, sometimes if you're not like really careful with it, you sort of pushing forward, like your head's going forward and forward and forward. And then right as you get to the stopping point, you kind of bob forward and back. The Bragg peak is like that for particles. Wow. It's that sort of last little bob. And that means that there's a higher deposition of energy in a very localized area. And if you have an event that's two electrons, they're both going to have this sort of stopping phenomenon. And so they're both going to have this relatively high energy at the end. Whereas if you have like a Compton event where you're producing only a single ionized particle, you're only going to have one of these high energy events. And so what you do is you look at your track, identify the two ends of the track, pick a volume, calculate how much energy is in that volume, and then compare the two. And if they both have relatively high energy, that's what a signal should look like. And if one has high energy and one has low energy, that's what a background looks like.
Wow.
So these are simulated versions, but that's what we're looking for. So then you can plot the comparison of the higher energy to the lower energy of the two, and signal events will look like what you have on the left, and background events look like what you have on the right. So this is the fundamental concept. And my work was dealing with these three-dimensional clouds and then reconstructing them so that you can identify where do you put the end location. Like, so I said, you find the end of the track. Well, how do you do that? Like, practically speaking, what XYZ position is the end of the track? Because all you have is this cloud of electrons. Like, you don't know. And a human can look at it and say, I want it there. But if you're having a human doing it, not only are you looking at tons and tons of events, but you're also introducing a bias. So you have to have a quantitative way to do it. And then how big of a volume do you pick? So here is
this would make a great crowdsource project on Zooniverse.
Yeah, we actually talked about that. We considered that as an option. Yeah. So this is my track reconstruction.
We've reviewed a bunch of those projects, and it's fascinating, all the different things people,
Yeah, so that's one way to do it. That's my work was sort of identifying where the ends go and how big of a volume.
Mm-hmm.
There's another potential way to do it, and this is what's called barium tagging. So there's a process called single molecule fluorescence imaging, SMFI, and this is a technique that's relatively widely used in medical research. It's not particularly well used in high energy physics, But basically what happens is if you have a particular atomic structure that can interact with the thing you're looking for, in our case, a barium ion, then it responds differently to light. And so what you do is you look for the initial signature, this initial little flash of light, and then based on that, you shine a light on a surface that's coated with this chemosensor. And if a barium ion has been trapped by this chemical, then you get a little point of light and you can see a single molecule. So this single molecule for us. So this is some of the chemistry behind it. Again, we have groups of chemists that look. So without a barium ion, it looks like the left, and then the barium comes in, looks like the right. So it changes the chemical structure, and then you get a response. And I am helping to produce a source for that. So this is some of the other work I did. So, okay, yeah, same stuff. These are track reconstructions.
Wow,
etc.
that was quite a project for your tastiness. My goodness. Yeah, you're still here. Yay. Okay, we got another question, and I think since we're at an hour, I'm going to go ahead and move on with the show a little bit. We got a couple of segments, and then we'll watch for comments. If you don't mind sticking around for a little bit, we'll get to those, and we want to make sure that people can ask.
Yeah.
All right, so Jessica says, how much data is a lot of data? Millions of rows, billions of rows?
Well, so it kind of depends on your perspective. So we have, let me check actual numbers. We have several thousands of SIPMs, and they are taking an image on the microsecond scale. So you have, and I forget exactly what the resolution of these SIPMs is. Basically, we're treating them as single pixels, though. So you can, they're not actually, physically, they're not single pixels, but we are treating them that way, so you can. So you could say several thousands of pixels per microsecond for 5 years. So that much.
That's a lot of data.
It's a lot of data, but we're not keeping it all either, right? So we're constantly scanning. And then if we see that initial flash of light, then we know, okay, this is a time window where we need to pay attention. So we keep this data. And then if there's just nothing happening, that we don't.
Yeah, wow.
Yeah.
Yeah, because you're talking several millions of pixels per second of data.
Yeah. Correct.
Wow. The mind reels.
Yeah.
All right, I'm going to go ahead and say that Everyday Spacer is sponsored by CME Computer and IT Solutions, and then Jeff will do some stellar events this week.
Okay. Speaking of some stellar events this week, February 20th through February 27th. February 23rd, Uranus and the moon are in conjunction, and Pleiades is 1.2 degrees south of the moon. February 24th is the first quarter moon, and the moon is at perigee, 229,989 miles away. On February 25th, the moon rides high and Mercury appears stationary. February 26th, Mercury and Venus are in conjunction. February 27th, Jupiter and the moon are in conjunction, and Jupiter is 4 degrees south of the moon. Also, Pollux is 3 degrees north of the moon.
That should be pretty.
February 27th is our Friday night show, and another audience request. Learn more in a minute. Find us Fridays at 9 p.m. Pacific time on the Everyday Spacer Facebook page and the Everyday Spacer YouTube channel.
What inspires you the most for the coming week? And if you or someone you know has done something interesting involving space exploration, science, or astronomy, we'd love to share our live. So next week, Friday, February the 27th, we got some requests about, I can't remember if it was like mining on the moon or Moon Miners Manifesto, which is a publication, or what, but we're going to kind of come at that from a couple different angles, and we'll talk about that as you were interested in finding out about it. So, all right. I'm so glad you're here, Adam. I can't wait to have you back. This was so fun. So interesting. We love the particle physics stuff a lot. We've done a couple of shows on that, and definitely IceCube, and I think there's a couple of other detectors that we talked about.
Yeah, they're building one in the Mediterranean. Yeah.
Oh, very cool. What's that going to be like?
I mean, it's very similar to the one in Antarctica. So it's sort of streams of strings of detectors covering an area. I think it's like just southeast of Italy.
But there's no
my
ice.
recollection. I want to say it's
there.
Dolphin, maybe. I don't know.
What?
If you look up Neutrino Detector Mediterranean, I'm sure you'll find
Got it.
data on it. But yeah, there are plans to build several of these neutrino detector arrays.
Interesting. So, how is it going to be? A similar size? Is it going to be water?
Yeah,
land?
I think it's probably not quite as big. IceCube has had time to develop. They've had one or two expansions, but beyond the initial proof of concept. And the nice thing is that once they sort of have the basics down, adding more is not terribly difficult. It's just scaling up the production and monitoring. I mean, it's a little challenging because it is literally at the South Pole, and they have to have scientists there year round. So they have, they have an overwinter crew that stays at the South Pole for, a year, which is kind of, one of my colleagues was really interested in doing that. It's challenging to get one of those spots, but yeah, it's kind of a neat experience, is my understanding. So the detector, like I said, they're looking at neutrinos that are interacting with the ice shelf. And they actually filter out they're only looking at neutrinos that are coming up. So they're looking at neutrinos that have passed through the planet and then interacted in the ice shelf, which is kind of cool. And the way that they calibrate it is so they're trying to see neutrinos that are coming from the sun. I mean, they look for all of them, but they look for ones that are coming from the sun for calibration, and then they look for dips in their response rate when the moon is between the sun and the detector station, so that because the moon will filter out some fraction of the neutrinos will interact in the moon, and so therefore won't be available to interact in this. So it's cool. So the ones they do see, then by definition have passed through the moon and through the Earth, and then interacted in this.
Wow. Yeah, that'd be neat to. I don't know. I'm kind of shy of the cold now.
Yeah.
Having lived here for a while.
Well,
yeah. But the scale is huge. I mean, like the detector covers something roughly equivalent to the area of Manhattan.
Yeah, it's kilometers.
In volume too, not just area. It's because it's these strings. It's like the vault with all the skyscrapers and everything. Like that's roughly the scale we're talking about.
Right. Yeah. Yeah, we definitely enjoyed that episode. And yeah, I don't know if you've seen some of the other ones on Zooniverse, but there's really they've taken 100-year-old textbooks and had us pick out, parts of them. That was really interesting. I mean, there's like such a wide range of projects on that site. We've only covered like the science and fiction and physics ones. I mean, there's like tons of stuff, like count all the little grasses in space, but that's very definitely classic science stuff that now they're getting help from citizen science. People can go out there and help out and do real science. It's amazing.
Yeah, I think the ongoing developments in AI are going to have a big impact in an area like that, because a lot of those concepts are actually very well suited to AI.
Right. Well, in fact, a lot of the Zooniverse projects are to train their AI.
Yeah, that does not surprise me.
Yeah.
Right. Yeah, because sometimes the people can do better pattern recognition type things, and the AI just doesn't quite get it.
Well, it can learn from the humans though. With, oh wait, this is a detection, and this one is not.
Yeah.
Right.
All right. Well, I'm gonna help wrap it up here because we really want you to help get your doggy. Jessica was here. We do a shout out sometimes. Jessica was here, and Donald and Naomi. And did we miss Scott? Where's Scott tonight?
Yeah, no Scott tonight.
No Scott tonight.
Dan's here.
Daniel.
And Janie and Cliff.
All right, we're good. Dawn was here. What a great crowd and great questions, folks. We really appreciate that. We really love having you here with us. It's always a better show when our audience is with us. Yep. So good night, Adam. And we'll talk again about coming back. And have a great week, folks. We'll see you later. Good night.
Good night.
Thanks. Bye.
Bye. Bye.